Hello there, Mr. Sutton here, bringing you the BC Calculus 8-2 Extra Practice number 5 solutions on arc length. For this problem, we're given the derivative of some function, and we want to know the length of the original function from x equals 0 to x equals 1.5. So this is one of those where if you know the arc length formula, you're pretty much good to go. So we're going to need the integral over this length here, so from 0 to 1.5 of, and here's the crux of the formula, you have the square root of 1 plus the derivative squared. So we'll write square root of 1 plus f prime of x squared dx. And now the rest of this is just going to happen on the calculator. To make this a little bit easier to enter and reduce my chances of errors, I'm going to enter my f prime as y1. And then let me quit out of there. I'm going to do Math 9 for integral. We're going from 0 to 1.5. And I've got the square root of, now we have 1 plus the derivative squared. So that's going to be alpha trace y1, because that's where I stored f prime. Square that and put a dx there. Press enter, and we get about 2.497, which is going to match answer choice B. For this problem, we have a curve in the xy plane given by the parametric equations x of t and y of t. The graph of x of t is shown here on the left, so this is just x, whereas y prime is this other graph here. So they didn't show you the actual parametric curve. These are kind of the components individually graphed out with respect to time. We want to know which integral expression here gives the length of the part of the curve described along the interval from 1 to 3. So we have to use our parametric arc length formula to do this. In general, I'm going to have an integral from a to b of the square root of x prime squared plus y prime squared dt. So that means we need to figure out what x prime and y prime are on this interval from 1 to 3. And it's going to be specifically on this interval here because these functions are doing different things at different places. So on the interval specifically from 1 to 3, what is x prime going to be? Well, x prime is just going to be the slope of the x graph on that interval. Taking a look at the x graph right here, on the interval from 1 to 3, just taking a piece of this line, we're going down 2 and over 1. So that's a slope of negative 2. So that is going to be our x prime of t on this particular interval. Now for the y prime, well, y prime is actually given in this graph here. So what we need for y prime is the equation of this line on the interval from 1 to 3. So this is just also a line in y equals that you could put in y equals mx plus b form. So we have an m value, a slope of 1. You're going up 1 over 1. We have a y-intercept of 1. So that's going to be y prime equals 1t, or just t, plus 1. And now to get the arc length out of all that, I need the integral from 1 to 3 of, and now I need the square root of x prime squared, so negative 2 squared, plus y prime squared. So that's going to be t plus 1 quantity squared. And of course, there's a dt over on the very end here for our differential. Now, unfortunately, this doesn't match anything they've given us, so we're going to have to clean this up a little bit inside and simplify. So we've got negative 2 squared, which is 4. Next, expanding this squared binomial, I've got t squared plus, let's see, multiply these and double it for the middle, so that's 2t plus 1. And then I can combine the 1 and the 4 to get t squared plus 2t plus 5. And that is going to match answer choice B. C is pretty similar, except there's that extra 1/2 out there that we don't want. So choice B. For this one, we have a curve defined parametrically by x of t equals f of t, and y of t equals just t. F is a differentiable function. Okay, that's good to know. We want to know which is going to give us the length of curve C from time -1 to time 8. So we need to figure out, for arc length here, we need the derivatives of x and y. X prime of t is just going to be f prime of t. We don't really know what that is, but we know that f is differentiable, so we can write f prime of t without feeling foolish. And then we also need the derivative of y, so that's going to be y prime equals 1. So now for the arc length, we're going to have the integral from -1 to 8. And here we'll have the square root of f prime of t squared plus 1 squared, which is just f prime of t squared plus 1, which is going to be answer choice D. For this one, we want to know which of these integrals gives the length of the curve defined by these two parametric functions from 0 to 3. So we already know we're going to have an integral from 0 to 3 if the answer choices didn't make that clear. But inside, we're going to have the square root of x prime squared plus y prime squared. So that means we need to figure out what x prime and y prime actually look like. So let me do the box and ribbon for each of these. These are both product rules. So for x prime, and we again have the integral from 0 to 3. For x prime, we've got e of t, or e to the t, and sine of t. So those derivatives are going to be e to the t and cosine of t. Multiplying that out, I'm going to end up with e to the t sine of t plus e to the t cosine of t. And that whole thing is being squared because we need to square x prime. Next, I need to find y prime and square it. So box and ribbon time again. Now I've got e to the t and cosine of t, whose derivatives are e to the t and negative sine of t. Multiplying that out with the ribbon, I've got e to the t cosine of t minus e to the t sine of t, and that whole parentheses is being squared. We have a dt out there. And which answer choice is this going to match? Looks like answer choice B. For this one, we have R, the region bounded by the graphs given here, which I'm going to refer to from here on after as f of x and g of x, because I don't feel like saying all this every time. And we want to know the perimeter of the region R. Okay, so to know perimeter, we need the arc length formula for each of those sides. So that's going to, in general, be the integral from a to b of square root of 1 plus the derivative of the curve squared, dx. So we need the derivatives of these functions. We also need to know where they intersect. We need to know this intersection point so we know what our interval is that we're taking that integral over. So let me figure out where f of x equals g of x. So here we go. I've entered f and g as y1 and y2, and I'm going to graph these. Now the window I'll use, well, it looks like this all goes from 0 to 4. In fact, 4 might even be the intersection point. I'm not really sure, but I'll find it out in just a sec. Let me go from 0 to 5. That won't hurt me. So let me do window 0 to 5 and zoom 0. So there's f of x. And here is g of x. And if I do second trace, option 5, and move my spider closer to that intersection point, we go 1, 2, 3 enters to get, yep, it is 4. Okay, so at x equals 0 and 4. So those will be our limits of integration. Now we're going to have the derivative of both f and g in order to use our arc length formulas. So for f prime, that's just going to be, let's see here, power rule, 2 times 1/2 is 1, so it's just 1x, and that 2 is a constant, so we don't worry about that. And then for g prime, that's going to be 6 minus 2x. So now for my arc length, I need the integral from 0 to 4 of, and this is actually for my perimeter now, I'm going to have basically an integral from 0 to 4 of the square root of 1 plus f prime squared dx, and I'm going to have pretty much the same thing but with g prime instead. Now since these are both going to be, well, let me just show you the f one first. So we have the square root of 1 plus f prime of x squared. Now, since these are both going to be going from 0 to 4, I'm actually just going to combine them into one big integral. So I'm going to add in here the square root of 1 plus g prime of x squared, put a big dx outside of everything, and this will basically cover having two different arc lengths formulas added together. So let me do the rest of this on the calculator. So to try to make my life easier, I'm going to enter each of these individual arc length integrands as y equals. So for y3, I'm going to have the square root of 1 plus f prime squared. Since f prime is just x, that's square root of 1 plus x squared. And I'm going to do pretty much the same thing. So square root of 1 plus g prime squared in y4 here. So that's going to be, let's see here, parentheses 6 minus 2x squared. And there's lots of ways to do this. This is just one of many ways. Now that I've done that, I'm going to quit out of there. Let me do Math 9 for an actual integral from 0 to 4. And now I'm going to do alpha trace y3 plus alpha trace y4, put a dx out there, and hope for the best. So all of that comes out to 20.520, which is going to give me answer choice C. For this problem, we just want to know the length of e to the 3x from -1 to 2. So I'll need my arc length formula for this, which is going to involve the derivative of y, dy over dx. That's going to be, using the chain rule here, 3e to the 3x. So then I'm going to have the integral from -1 to 2 of the square root of 1 plus this derivative squared, dx. And I have to match one of these answer choices, so let me just simplify this a tiny bit. So I have to square both the 3 and the e to the 3x. So that's going to be 9e to the, we have to multiply the exponents, so 6x inside that square root, which ends up giving me answer choice D. For this one, we just want the length of the curve y equals x squared plus 2x between x equals 0 and 5. So I'll need my arc length formula, which is essentially the integral from a to b of the square root of 1 plus the derivative squared. So I need the derivative for this. That's going to be 2x plus 2. So now we'll have the integral from 0 to 5 of square root of 1 plus the derivative squared. So square root of 1 plus 2x plus 2, that piece of it squared. And does this match any of the answer choices yet before we go ahead and simplify this? Well, it looks like it does. This is going to be answer choice C.